I'm Odin Holmes. I have gotten bored of introducing myself in any sort of normal way, so this is a superhero origin story. How I became Odin the Nerd, because I was originally instantiated as Odin the Hippie. And that's kind of a different type of object. I'm an object, but no, anyway. This talk is about abstracting things. So let's get some practice on sort of abstracting things. This is the abstract hippie. This is, if you know, this is the Spanish story of a knight that went crazy and started fighting against windmills and whatnot, Don Quixote. And this is the abstract hippie because every hippie wants to change the world, and they have all this valor and all this energy goes into it, but they're often very misguided about how to do it right. And I noticed this as a hippie kid because, even though they were fighting against nuclear power and whatnot, it seemed to me that if we were to, as sort of a thought experiment, think back 200 years ago to that technology level, and if we had that today, probably 95% of the world's population would die, right? So who is saving the world? Well, the nerds, of course, right? It's one of the most philanthropic things you can do with your life. So the nerdification process began. And one large part of my nerdification process was actually this book, and by our keynote speaker. And this was my first C++ book. Before I finished it, I had to read other C++ books in order to understand it. But for a while, I thought this was how you write C++, and I just wasn't very good at it. And I didn't have C++ in school because I just went through high school, and then I started a company and didn't go to college. And so I completely self-taught, and I figured, well, why don't we sort of abstract the learning process, as in the true learning process of learning new things that nobody else knows, right? You think of something, and then you try and implement it, and oh, this is a lot harder than I thought, right? And then you say, hey, look at this thing, and everybody else goes, oh, that's wrong, and you go, shit. And then you try and fix it, and then you just repeat that forever. So what am I thinking about in this talk? We have sort of a common problem in C++. We try to be zero cost, and most other languages don't even try, right? Because it's a hard thing to do. But we aren't quite zero cost, I would say, because if I'm using a shared pointer, well, do I really need weak pointers? I mean, the weak reference counter is taking up space in my object. I don't always need weak pointers, right? Maybe I know that this shared object is only going to live within a certain thread. Why does the ref counter have to be atomic? Why can't it just be a normal counter, right? There's several other things you got to do. Do I need a type erased custom deleter? Do I need both the functionality of make shared, where I can put the object next to its control block, or the functionality of being constructible from a pointer, where I can't do that, right? Maybe I want all of my team to always use make shared. Why can't I just take the functionality out of being able to construct it from a pointer? Maybe this shared pointer expresses a shared resource which is rebindable, as in I can make that shared resource point to something else, but never null. Maybe it's not optional, right? Maybe I want to make my shared pointer only constructible in a sort of a make shared way, and therefore never empty. If you think about shared pointer, well, if you think for about 5 minutes about what a shared pointer is, it's a bunch of different functionalities. And I thought about this for about 5 minutes. And if you think for another 5 minutes, you probably come up with reasons that it's wrong. See previous graphic. But in some sense, it would be nice if we could just compose a shared pointer out of all the stuff we want and all of the stuff we don't want, right? I mean, who here uses something that's like a shared pointer but not standard shared pointer in your code? Most people. Actually, very few hands. I'm going to have to ask some other questions and just figure out if people are shy or if you're all just using shared pointer. But yeah, there's a lot of code bases that have a lot of things that are like shared pointer but not quite because somebody had one gripe with shared pointer. Maybe I want to make my own shared pointer with a lot less stuff in it. It's constructed in different ways. It acts differently. And if you go, the standard function, in place, vector, in place, well, there already is a small string operarization, but I can't say how big it is. I can't really do an in place string. There's all sorts of different proposals in the standard committee. Most of them actually in the SG14 working group, which I'm a part of, which have to do with making some standard function, standard library container or functionality a little bit different so it fits our use case better, right? I have an array which has a fixed capacity, fixed size. I have a vector which has a dynamic capacity, dynamic size. Maybe I want fixed capacity, dynamic size, as in it can grow up to X, but it can also be smaller, right? It would be nice to be able to sort of compose those out of pieces. Standard function is a good example. Standard function has a small object optimization, and if you're working in a multi-threaded context, you implicitly rely on that, right? You may not know it, you may not have realized it, but your code will run very much faster or slower depending on whether you're in that small object optimization size or not. And all three standard libraries currently agree that it's the size of 3 pointers on that particular platform. And so if your objects are smaller than that or that size, then they will not go on the heap. And if somebody, for the sake of pissing people off probably, makes that the size of 2 pointers, then a lot of code will suddenly run so slow that it's essentially a breaking change, right? Why can't I specify how big that small object optimization is? What if I have an object that's the size of 4 pointers and I don't want it to go on the heap? I mean, you used to be able to play around with allocator, but that never really worked well, and that's deprecated now. Why can't I just make that buffer bigger? Well, because it's not part of the public interface. You'd have to hack around in the library. So the standard library sort of strategy for dealing with the fact that everybody has a slightly different use case is to fight about it until we figure out what the sort of mostly common goal is, and if something's dangerous, well, that gets prioritized to not go in there. And yeah, there's another. There are actually several other strategies to deal with this. We have Qt or Qt. I don't find it quite cute, so I'm going to call it Qt. It deals with sort of the customization, generic composition in a very different way. You can use Qt objects in a very generic manner. You can customize them and so on and so forth. The problem is that this is built on virtual functions, which are not efficient, right? So if we look at this, is everybody familiar with how Qt programs are written, at least widget style? Not so many people. Yeah, some people. So I'm going to go into this in a little more detail. So this is some dialog box that we created, and it's actually a composition of maybe a vertical widget, which basically just has 2 panes in this case, one at the top, one at the bottom, and then in those 2 panes we have more widgets. We have maybe a grid widget, which has 4 more panes, and then in this pane we got another horizontal box widget, divides it into still more panes, and then we have probably another vertical widget here, and then this is probably a composite widget built out of a label widget and a text field widget and so on and so forth, right? So if you think of this in sort of a reacting to events kind of a model, the event from the operating system will come to the very root of this tree of widgets, and it's just going to follow all the virtual function calls all the way down to the end. And this is a repaint event. They're probably interested in this event. If it's a resize event, these buttons are not going to change size, right? But there's no way for the compiler to know that we don't care about a resize event, because it's all hiding behind a bunch of virtual functions. So just for this dialog, if there's an event that nobody's interested in, then it's going to call 500 virtual functions or something for the sake of argument, right? That's not particularly efficient, but it is, it is very ergonomic. It's easy to work with these widgets. But if you think about key press events, well, that would just be overkill, because every time you pushed a button on your keyboard, every virtual function in your program will be called, essentially, right? Or at least one virtual function per widget in your program. So that's not how key press events work. You have to actually subscribe to them somewhere and handle them differently, which is not so ergonomic because they didn't have, they couldn't write code in such a way that the compiler could see through it and optimize away all of the things that were not interested in that key press event. We also have the sort of signal slot mechanism, which is, if we click here, for example, then we change this box to bold. And that would automatically update this box, right? So these two widgets are connected to each other via a mechanism called signals and slots. And to actually tell this widget, hey, here's your updated text, we go through 3 or 4 virtual functions in the Qt case. But it's known at compile time, like that this guy wants to call that guy, that's not something that's determined at runtime. We know that at compile time. We just didn't have the syntactic means of expressing that. I mean, there are a few things which you do change at runtime. So we still need the old interface and the old virtual functions and whatnot. But the stuff that we do know at compile time would be nice to be able to express that in a compile time readable way so that the optimizer can see through it and optimize our program. Yes?
How do you know that the compile time is a part if this window is created dynamically at runtime?
Is it created by an algorithm, right? Like you could, okay, this window could be, nude at some point for the sake of argument. But the layout of this window is probably known at compile time, right? Like if you look at most Qt programs, I mean, there are counterexamples, yes. And we also support the counterexamples. We'll see later. But let's see, would you be happy with the statement that there are compositions of Qt widgets that are known at compile time? Yes, we can work on that. If we were thinking about sort of ways of expressing this at compile time, we could express it somewhere close to the way you express the compositions of Qt widgets now, right? You have some dialogue. In the dialogue, you have a layout. In that layout, you have another layout. In that layout, you have, some bunch more widgets, right? In the bottom layout, you have a stretch and push buttons, whatnot, right? We don't actually need the virtual functions. The question is, how do we make something that can generically compose all these pieces correctly? How can it do all the plumbing, the glue code? And we also have this awesome thing called template metaprogramming. The thing with TMP is you don't really have to understand how it works to understand this talk. And who here is sort of played around with template metaprogramming? I know Arno has, even though he's not raising his hand. But yeah, only a few people. Well, so for this talk, and for actually a lot of contexts, you just have to understand that something is being done and that you can do that, and not really how. So for the other people that didn't just raise their hand, here's an alternate definition of TMP. It's Tabea Marie Paul. There are 3 magical unicorns that live in your compiler and do whatever the library author tells them to do, right? But let's look at another problem, because this is actually the problem that I designed this abstraction mechanism in order to deal with. And it's embedded drivers, as in drivers for serial ports on microcontrollers, right? Because this is a domain where I don't care how sexy your program gets. If you start writing abstractions, they have to be 0 cost or they're out, right? Like if you're designing this clicker thing, they probably sold tens of millions of these. If you're designing a mouse, they sell billions of them. If you can save 1/10 of a cent, you're rich, right? So, I don't care what abstraction costs, how small it is, it's too much. And so the embedded domain has had this problem since my birth, essentially, where the rest of the world said, okay, very, very small cost and we can have exceptions. Very, very small cost and we can have virtual functions, whatnot, right? But it's not zero. So they stopped sort of, the way you program tiny chips in C or C++ is pretty much the same way you did when I was a hippie kid, right? It hasn't evolved much, in my opinion. And so this is step 7 of a 17-step Hello World tutorial. And then this is not just somebody, so this is a chip manufacturer's Hello World tutorial for their chip, right? Like they didn't pessimize it on purpose. And so this is another way of abstracting things you just kind of don't, right? You spill all your guts out into the public interface, and then everybody can customize however they want because they can see all the guts, right? Which kind of defeats the whole purpose of abstracting things. So yeah, this is sort of initializing a serial port so that we can write Hello World. And this is how I'd like it to be. Because this is actually the inherent complexity. These are the only, I mean, if you look at this, almost everything here is default, right? Okay, 1 stop bit, 8 bits of data, right? Like these are standard values to a serial port. So why don't we just leave out all the defaults, all the normal stuff, and just write the stuff that we're doing differently. We can see, oh, we have a blocking interface. Who caught that on the previous slide, right? I mean, it's right there. It's blocking. And this, okay, we're being cute with some syntax as a user-defined literal, so this has got to be, C++ 14. We're abusing the fact that the copy constructor doesn't actually have to return a copy of that class to do sort of name parameter-ish stuff. But let's make this work. After all, I read that book by Alexandrescu, and he described something called policy-based class design, which you can use to compose things into other things. Build a class out of parts. So this is a picture that my wife took of me about 2 years ago. He's good with a camera. And so I started policy-based class designing drivers. And I was actually quite successful at it. I wrote a USB driver where you could just throw in, like, I want to be a human interface device endpoint. Oh, and I also want to be a serial port. Okay, now I'm a composite device. And it worked. There was a lot of sort of being here in the implementation. Oh, shit, that's harder than I thought. Oh, that's harder than I thought. And it ended up a proof of concept. It did work. It did drop less packets than the ARM embed version, and was 1/10 of the size and half the RAM footprint and so on and so forth. And also comparing it to a lot of the chip manufacturer stuff in C, we totally beat C. But problem was, I was very proud of this and wanted to show it to people. And there's a conference that's coming up next month in Bochum where we talk about C++ on microcontrollers and library design and whatnot. And I showed it to people there. And I showed it to Joël Falcou. If you don't know who he is, he's a French guy who seems way bigger than he is because he's always gesturing at the limits of his arm gestures and is very outspoken. Advantage to him is he will speak his mind no matter what, right? So he basically said, Odin, you screwed up. Third thing he said or something on the topic, right? You screwed up because I can't read your code, and it's not my fault. No one can read your code. You won't be able to read your code in the future. So yeah, I was here, right? And he was right. Or in the Don Quixote analogy, gallopy, 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 smack, windmill, right? Or, this is an excerpt of my code, which I don't really know what this is doing anymore, but I inspired some artist to do a picture of my code. And so at least it was good for something. But if you think, why did I fail, right? Why did I screw up? Like, why didn't it work? I put a lot of effort into it. Well, the problem was, in pictures, I built this toy, right? Which looks pretty generic if you just look at the little components that can go in there. But it's actually not so generic. And there are some limits to what policy-based class design can do. Okay, we didn't have variadic templates back then when Alexandrescu dreamed it up. We, didn't have a lot of sort of the compile time of template metaprogramming written in a modern style has gone down by 3 orders of magnitude or something since then. So, we have bigger power tools, and we want Legos because Legos are cool. Not new Legos. New Legos are not very generic. You can just build like one scene from Pirates of the Caribbean and then you can throw it away. But old Legos, you can build anything out of old Legos, right? So we want old Legos, something completely generic, which is more powerful than policy-based class design. And I have a history of naming things wrong, so I figured, okay, I'm not going to come up with a name for this. I'm going to steal a name for this. And there's this whole other field of Industry 4.0, blah, 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 where factories are going to assemble themselves and everything's just going to work and the robots are going to talk to each other and they're going to have lists of, oh, what are you capable of? Oh, I need that. And then they're just going to self-assemble. And I'm not quite buying into that utopia yet, but yeah, they come up with some pretty good terms. So these are all agents, and agents have abilities and requirements on each other. They kind of self-assemble. And yeah, I mean, my opinion on sort of this sort of very high level, let's figure out how the world works before we actually built it. Some people hacked this whole system, right? People in academia, they realized, I don't want to look like an idiot, so I'm just going to go down to this line. I call it the PowerPoint line, right? So, so you develop things up to the PowerPoint line, and you leave all the looking like an idiot to us engineers, right? So yeah, on a conceptual level, what are we doing here? Well, we have this component called an agent. This agent has requirements, socket symbols, has abilities, the ball symbols, and this is not a valid set of agents because there are requirements on other agents which are not fulfilled, right? A little bit of theory here. We'll get back to code in a minute. Theory, yeah. So this is a valid set of agents. And by the way, if you hadn't seen The Matrix, I'm sorry you're not going to get any of these jokes. So we have, a group of agents, and all of the sockets, all of the requirements have other agents with that ability. So it works out. We have a couple of extra abilities, A, B, and F. Nobody's using those. That doesn't matter. So how would this look in C++? We want to be able to just compose an arbitrary set of stuff and then tell the whole thing to, well, what do agents do, right? They kick Neo's ass. Again, if you haven't seen The Matrix, I'm very sorry. One of the problems that we have in policy-based class design is how do the policies talk to each other without the outside world seeing the implementation details, right? And this is, I think Alexandrescu said in the book, yeah, most of the stuff probably should be public or something to that effect. And that doesn't work so well in practice. So what we want is to have an arena where all of our agents go into, right? And all of these agents cannot be seen by the outside world. They can see each other, they can find each other based on abilities, and the outside world can't see them, right? So what is an agent? Well, an agent is just anything, basically, right? There are no requirements on what an agent is. But we do have to say what its abilities are. So we can wrap it in, some agent wrapper, give it a set of abilities. Agent Smith is obviously capable of ass kicking in this case. And then we have, the public interface portion, right? How do we reach into this arena of agents and provide the public interface to the rest of the world. Because in policy-based class design, public interface and implementation are the same class. But in this paradigm, there are two different classes. I can add things to the public interface, and I can add functionality to the core, and the public interface, again, will just find agents with the abilities that it needs to be able to execute whatever the user wants from us, right? So the public interface is not quite clean, right? We can see that there's some unicorn work going on here, right? You know, the pointy horn operator, and you can see the unicorns are there. So the requirement on a public interface class is you take a template parameter and derive from it. That's all, right? And because you derive from this template parameter, somewhere down there, there's some secret sauce that gives you functions like for each, with which you can say, okay, anybody that fulfills this ability, I want to execute this lambda on them, right? I get the agent, you know, these are polymorphic lambdas from C++14. So A is of some type, different type every call, or not, depending on, you know, what types you call it with. And we can you know, pass this user intent on to the actual agents. If the agents want to find each other, and we had this sort of just magical ability to call for each, right? If one agent wants to call something on another agent, if it needs other agents to be able to provide this functionality, it needs something on which it can call for each or find other agents with. So we have just this magical factory function called agents, which gives us, for the sake of argument, a bowl of unicorn soup, which we pass on to the agent call, with which it can go and find still other agents, right? So we can just propagate this ability to call anything in the composition on from function to function to function to function. I mean, if you understand the alternative meaning of template metaprogramming, or TMP, then it's a pointer with a whole bunch of type information, right? So, you know, one agent takes parameter agents, can use that to talk to other agents, right? And then, obviously, we don't always want to do a for each. You know, for each is also part of the, essentially, the contract of what is a valid set, right? If I say for each, then there can be 0 to n other agents in that set, and I'm still a valid set. What if I just want 0 or 1? Well, I can do sort of an optional, right? Rather than writing for each optional, that means either there's 1, in which case this lambda gets executed, or there's not, in which case nothing happens, or I can also do a fallback. If there are no other agents in the set, then you know, I can fall back to some alternative functionality, right? I can say there's got to be 1 and only 1. I just called it execute for the lack of a better term. Like I said, I'm bad at naming things. So there's not a whole lot of magic going on here, right? Like the public interface class is okay. They got to derive from the parameter, and I got to use polymorphic lambdas, and that's about it. So this is pretty user friendly. But where does the magic happen? Like if we want to go and look at how this actually works, let's look at that compose function, right? That bound everything together. Well, this doesn't actually have to be a factory function in C++17. You can make a templatized constructor, which will do the same thing, but we want to be 14 compatible. Essentially what we're doing is we're taking a variadic pack of 0 to n agents, public interface classes, whatever you throw at us, and we're making a tuple out of them and building an object called composed and sticking that tuple into that object. Right? So let's look at composed. Well, here we're getting to sort of the unicorniness, right? Which we're not really going to go into. We have a tuple where all the agents live, right? This is different than policy-based class design, where we'd be deriving from all of our policies, because that means that a copy constructor may be hard to write, and that means that you could maybe slice it, and so on and so forth. We're putting all the data in an aggregate, so no slicing possibility. So copy constructors basically, if it's copyable or not, if it's no except copyable, swappable, whatnot, I don't care. Tuple does all that for me, right? So what's this make base? Well, all of the public interface classes, they do need to be base classes, otherwise they can't add functions to the public interface. So what I'm doing here, what the unicorns are doing for me essentially is I'm taking some magic class called access, right? And I'm passing it to the first public interface class, which derives from it, right? And then I'm passing that to the next public interface class, which derives from it, and then the next one. And then up at the top level, compose derives from that. So we have this chain of compose derives from the first public interface class, derives from the second, derives from the third, or the other way around, I don't care. And that all derives from this magic class called access. And in access is where we have the for each, we have the optional, we have all those functions. And access actually also takes the template parameter of composed. So it's the curiously recurring template pattern just drawn out with a bunch of classes in between. So in access, I can take my this pointer and cast it to the pointer of composed because I know what type that thing is, right? And then I can access data. Well, I can't here because data is private, so I have different access, right? So this access class has all of its member functions like for each and whatnot protected so that all of its all the interface classes derive publicly from each other. So anyone in the chain can access the functions from the access class, except that we don't want people deriving from our composed object and accessing them. So we make them private at top level. Nobody can get in. We have essentially perfectly encapsulated set of functionality. We've closed up the arena so that people from the outside can't see our data, which you can't really do in policy-based class design. We also have some extra functionality for construction and destruction because there's still some things that I want to do that I couldn't express otherwise. What if I have in the constructor of one class, I need to say allocate something on an agent which is some general purpose buffer, right? Then I need to allocate on the buffer on construction, which gives me some kind of dependency. And I don't want the user to have to express what dependencies there are between the agents because that would get messy in the public interface. So we have the general problem that when we call a public interface class, at that point in time, the point of instantiation or the knowledge of the whole class layout is known. So we can do curious recurring template pattern tricks. We can essentially reflect on all the agents which are in this composition. But the constructor's point of instantiation is before the end of the top level class, right? So we don't know all of this stuff yet. But we do know what it will become. So we can just make, the tuple is up here in the dots. The tuple's already done. And that's all the information that we need to be able to initialize these things, right? So we can just make an ability I require in it in a destruct, and then call all the things without ability, and then they can just, so it's two-phase initialization. 2 is actually not a number. The only numbers that exist are 0, 1, and infinite, right? So two-phase initialization is not perfect, but it's the best that we can do so far. It does work pretty well in practice because you usually don't have like cyclic or complex dependencies. It's usually just thing A depends on thing B. Okay, cool. So with this, we can solve a lot of other problems. I designed this for generic drivers, but there's a lot of other things you can do with it too. I had a really cool bug. Somebody on my team came to me and said, yeah, I want to convert a string to upper on this microcontroller. And I looked at Stack Overflow, because where do you go to look for stuff, right? And this is a very, very upvoted answer. Use boost to upper. And I'm getting this linker error. And I don't understand why, because I can use other boost functionality, and I've reduced it down to, essentially just this. And it's not working. And if I comment out the whole boost to upper part, string, no problem, right? So the linker error was that the chip was full. Not only flash, but also RAM, because this to upper, well, uppercase, that could be locale dependent. Locales pull in, you got locales, you got the heap, you got date time for some reason. I don't know why that got pulled in. You essentially got most of libc got pulled in by just doing this, because you could be in a multi-threading context, right? Locales need a lock, locks need threading infrastructure. I got one core. I'm not running threads. I don't even run a schedule. I don't have a heap. Why? Right? So this is kind of the inherent complexity of two upper if you're one of those crazy America First people, right? No, but for ASCII, this is the two upper. If we can start there and say, okay, the ASCII letters plus, I don't know, Swedish. We'll just add the Swedish letters to that because, I make, I don't know, furnaces. I don't need to sell to countries where it's not cold, right? This is a country where it's cold, by the way. So maybe I need to add to this interface because some letters can become multiple letters when they're switched from uppercase to lowercase or lowercase to uppercase. And this is a generic interface. I have sort of a range coming in, range going out. I eat stuff out of the input range until I consider that a code point, and then I spit stuff into the output range until I'm done. If you think about this, well, I could make a lot of composable bits that fit this interface. I could format things, right? Just a bunch of different agents. One of them has a two string, or I just called it string, and all the formatting happens when you call that function, right? If you get back to drivers, this seems perfectly implementable, right? I have a bunch of different agents. They all compose, connect to each other. And as a user, okay, maybe the library gives me this, but as a user, I know, hey, my UART has this special functionality called Autobot, which basically just means look at the bits, the shortest thing, the shortest transition you see, that's probably 1 bit, because why would there be anything shorter than that on the bus, right? So I can write my own agent, which has the Autobot capability, compose that in, and the advantage of this is that I know whether the user is using it or not. The optimizer doesn't know if some branch in the interrupt service routine can ever be taken, because whether or not that can be taken is some other bit in some other register that turned on or off that functionality, right? So I can beat C because I know more than they do, right? If you think about the statically linking widgets example, well, a widget is a composition of agents, and we can just decorate that composition of agents with more abilities, and it too can become an agent in a higher order composition of agents, right? So the public interface of one composition has things like handle event this, handle event that. That can be an agent in a, some layout that takes multiple agents of that, and you can just build a whole nested tree of them, right? So we can write Qt to a certain extent. Oh, I called it Qt. To a certain extent without all the virtual functions. This would be essentially the factory function for a box layout, right? I take the abilities that I'm presenting to people upstream and the interface that they want. I have a policy that just forwards all the events to my children. I have some visible, maybe, area, and then here's where all the widgets go. Right? I have to rest this a little bit, I'm sorry. But coming back to your question, what if I want, these 5 composed widgets into some composite widget to act as a dynamic widget for people upstream, right? What if I want to be part of some dynamic composition? Well, Sean Parent came up with this concept-based polymorphic wrapper where you can wrap things that fulfill a certain interface and present an interface to the outside world. And then Gasper Usman came up with a way to build this out of composable pieces, and we can just annotate our public interfaces with the composable piece that can make it polymorphic, and then compose those pieces, and every composition of widgets that fulfills that public interface is now polymorphic. We can just add polymorphism from the outside, and then we can mix virtual function-based generic programming with compile time generic programming. We do have a problem with initialization through constructor, but I'm going to skip that because I'm essentially out of time. I'd like to also thank Gasper for his help with coming up with this. Basically, he just asked me questions that I couldn't answer, and that was worth its weight in gold. So yeah, I solved the world, right? Not really. I'm not in academia. I'm actually an engineer, right? So I didn't solve the world. I have to figure out how do we test this stuff, right? If you have essentially infinite combinational complexity, it's hard to write unit tests for that in any sort of exhaustive manner, right? We have contracts between agents, but if there is some flaw there that didn't show up in the sort of I test that agent in isolation, then that's going to be hard to find because it's only going to happen when the user composes some certain set of agents. We also have the problem of, let's think about a toolbox of agents with which I can build a container, right? I want to build a vector which can only grow up to a certain limit. And maybe with the same components, I want to build a vector that is just like the standard vector, right? Well, the standard vector version, I'm going to have in sort of my, keep track of things agent, 3 pointers. I need begin, I need size, and I need end. End and capacity. Well, in the case that I just have a buffer, and I can't grow beyond that buffer, and that buffer is part of my object, I don't need begin, I know where it starts. I don't need capacity, I know where it ends. I just need size, right? I need to know how much of that buffer have I filled. So depending on other agents in the composition, my memory layout has to change, right? And again, that's a hard problem because we can't use the trick of the point of instantiation being later. The memory layout point of instantiation is immediate, right? But what we can do, what we've been playing around with recently, is have, rather than just agents, allow agent factories where you pass in some dummy object that will give you the resulting agent when passed all of the other agents in the set, right? So I would take the parameters of all the other agents. I would say, oh, look, there's just a fixed buffer, so I just need the small version that only has 1 pointer rather than 3. And then if I'm in the meta domain, I can say, well, okay, how big is that thing? Maybe I can represent that as an index, which is smaller than 32-bit pointer, right? Those kinds of things. That can get quite complex if I have a lot of interdependencies. And again, how do you test that, right? If thing A relies on thing B, and thing B wants to reflect on thing C, and so on and so forth, and I have this huge dependency graph, I have to make sure there are no cycles in it, right? So yeah, this can get complicated. In practice, I haven't seen it yet. And we still have the age-old problem, which Alexandrescu noted in his book, decomposing things is hard, It does take a while about thinking about a problem to tear it apart into all its little pieces and make it work. But sort of initial work in this domain has been actually quite promising. We've been able to make even more efficient drivers, and you can read the code. Yay. So if you want to talk to me about that or anything else, I have Odin the Nerd at basically everything, and come to Embo. Questions? Yeah, or a clap, and then questions.